In the last video, we saw some of the hidden pitfalls of using raw pointers in modern C++. Today, let's look at how to systematically tackle those issues in a way that would actually hold up in a real code base. Welcome to the third episode of Learn C++ with me. Tackling these issues, I made my own smart pointers. Imagine Santa is with us today and he wants to create a list of postcodes where all the nice kids live so that he can deliver goodies this Christmas. Santa is special. He does not write program that leaks memory. So, in our example, the postcodes are stored in a raw integer pointer called list wrapped in a class called NiceList, and we have member function print start point that prints the starting point of Santa's itinerary. The pushback function is responsible for handling this raw resource list. On every call, it allocates a new array of size plus 1, copies the existing list into it, deletes the old array, points the list to the newly allocated memory, writes the value and updates the size. The member function print_start_points prints the starting point of the itinerary. Let's step through the main runner code. We start by declaring an object v of NiceList. Into the list, we push addresses 1, 2, 3 where the nice kids live, and then we print the starting point. Let's compile the code and run it. And it seems all right, but what happens to their list when v goes out of scope? I'll take the help of Python visualizer to step through the code. If we step through this Python tutor, we see v on the stack, and as we step through it, its constructor initializing the list to null pointer and size to 0. Each pushback call allocates a new buffer. Copies the old contents, deletes the old buffer, and returns. So far, no leaks. We do this one more time. We allocate a new buffer, copy the content, delete the old buffer, update the new value, update the size, and return. The problem appears when the program ends. The object v goes out of scope after printing the address. The stack frame disappears, but the heap allocation stays. That's a memory leak. This leads to the first rule of handling raw pointers in C++. Always write a destructor. Once we add a destructor, to this simple program which deletes the list, the memory leak disappears for this simple program. Let's visualize the final steps again. As we step through the last line, the destructor is called. It deletes the array allocated on the heap, and we don't have a memory leak anymore. The first rule of using a raw pointer is always write a destructor. That done? Easy enough. Now, Santa wants to share NiceList with his elves so that the elves know that where they're supposed to start distributing the gifts. Now, in this part of the code, suppose an elf creates a NiceList W which copies V, does some processing on W, prints the start point, and then goes out of scope. Santa then checks the starting point again and he goes out of scope as well. This should work. Let's compile and run the code. So we compile it and we run it again. But when we run it, the starting point for Santa's itinerary becomes garbage and we get a malloc error. Can you guess why? Let's visualize and see. For clarity, I have just pushed one address into the list and we step through it. First, Santa creates his list. Then the elf comes into the picture and copies the list, prints the starting point, and then goes out of scope, alongside deleting the list for the Santa as well. Visualizing again with Python Tutor, we see that W just copied the pointer and size from V. When W is destroyed, its destructor deletes the list. Later, when V is destroyed, its destructor tries to first read from the destroyed list, and that's the garbage value, and then when the program ends, it tries to free that memory again. That's a classic double free. Now, how do we resolve this? This gives us the second rule. Always write a copy constructor when your class manages a raw pointer. A proper copy constructor must allocate new memory for the copy and duplicate the contents rather than just copying the pointer. So now let's implement the copy constructor. This constructor will copy the value from another object which we are calling RHS. This is the V over here. So yeah, these are the default values that this object has. So when we implement a copy constructor, it takes the right hand side object, it allocates a new array of the same size. So this is the key part. Yeah, or we can just do it over here. And then it copies the element from the original list into the new one. The original list into the new one. So list is the pointer inside of the new object W that's created. And that's it. One point to note. In our example, the list is one dimension. So the deep copy is straightforward. But suppose instead of the list it were a matrix, then we would need to allocate new memory for every dimension in the original object. Once we add this copy constructor and run the program, the output is correct and there are no double frees. Let's try it out. Sorry, this should be RHS size. You see? Let's visualize this in Python tutor. So first we create the list V, push an address into it, then the elf creates a list W, and now crucially, instead of copying, it goes to the copy constructor, which allocates new memory, copies the element into the list, into the elf's own list, and then goes on. When the elf goes out of scope, only its copy of the list is deallocated. And finally, when the Santa goes out of list, we deallocate the original list from the heap. And we end the program without memory leaks. It might feel like the job is done, but there's another trap. Suppose an elf independently starts to build its own NiceList, like so, and then later discovers Santa's list and decides to reuse it via the assignment W equals V. This is no longer a copy construction. It is a copy assignment, and the rules change. When we write W is equal to V, by default, we perform a shallow copy of the pointer. That puts us back in the same situation as before. Two separate objects, the elf's list and Santa's list, owning the same raw pointer and both trying to delete it when they go out of the scope. Let's compile this and run this version. Once again, did we save it? We didn't save it. Once again, we get corrupted data and an allocation deallocation error. To understand why, it helps to step through the code in Python tutor and watch both V and W. Okay, so let's step through the code. First, the list of Santa is created. Then the elf independently starts to write its own nice list, very presumptuous of it. Finds that Santa has already created a list and decides to reuse it. Uh-oh. Goes out of the scope, deleting the list. And once again, we have allocation deallocation error. To fix this, we need to write our own copy assignment operator. The idea is similar to copy constructor, but there are some. So the idea is similar to the copy constructor. We are overloading the assignment operator. What we need to do is to allocate new memory of the same size and copy all the element from the sources list into this new array. But there's one subtlety. The original list, which the elf might have already started to work on, must be deleted so that we don't have a memory leak. If we forget, that becomes a memory leak. And if we delete it too late, we might lose track of what to copy. So let's write the delete while we still have the address of the original list. With this version in place, we compile and run again. The program appears to work, and when we visualize it in Python tutor, we can see that V and W now own their separate arrays with identical contents. So let's visualize this. The elf starts to work on its own list. And now, crucially, when it decides to reuse Santa's list, it takes us to the copy assignment, deletes the old list which it had, creates its own copy. It creates its own copy of the list and then carries on. When the elf goes out of the scope, it only deletes its own list. And when the Santa goes out, its own destructor is called. All is good and well. Copy assignment in C++ is trickier than it looks because the language allows chained assignments like x equal to y equal to z. In such expression, y equal to z must return something that can be assigned to x. Like so. Suppose there are two elves, x and y, who copy from Santa's list V. Then, if our copy assignment operator returns void, which it does right now, then y equal to v yields void and x equal to void does not compile. We can try it out as well. It throws an error, no viable overload for equal to. That is why in the idiomatic signature, we must return a reference to a NiceList object. But where is this reference? What should this reference be in our case? the caller should get a reference to the object which is currently being called. And inside a member function, the keyword this is the special pointer that refers to the current object of this instance. And that is what we must return. Believe me, I was as confused as you are, but it gets easier when we visualize it. So for now, we can see the error is gone. There is one more edge case, self-assignment. Consider the statement V is equal to V. Santa just wants to match his own list with itself, with himself for some reason. He just wants to copy his own list. If our assignment operator blindly deletes the current list first and then tries to copy from the right hand side, we have a problem. The source and the destination are the same object. Deleting the list destroys the data we are about to copy, which leads to crashes or garbage value. Running this scenario and visualizing it shows that the pointer is freed before we read from it. Let's save the code, compile it, run it, and we can see we don't get the expected output, which should be 1. Let's visualize this bit. First, Santa creates his own list. Then two else x and y copy from it. First, y copies from Santa's list, which we already know, which we have already seen earlier. Notice the reference to the object is called this. And this reference is what is returned for the next assignment, y equals to x. So the RHS in this case is this pointer which was returned by y. And now we go to self-assignment. Both this and RHS point to V. We delete the list. Uh-oh. And then we try to allocate something new. But what are we actually copying from? We are copying garbage into garbage because RHS and LHS are same. And that is where our 0 was. 0 was the garbage value. So how do we guard against this? We must check if the right hand side and the left hand side refer to the same object. If they do, if this is the right hand side, then we do nothing. We just return the same reference. Otherwise, we proceed as usual to copy, delete, and update. With this, the classic rule of 3 for owning raw pointers in C++ is complete. The 3 rules are: number 1, write a destructor to release the resource. Number 2, write a copy constructor to perform a deep copy on initialization. And number 3, write a copy assignment operator that handles the deep copy, chaining, and self-assignment safely. In the next step of this series, my plan is to see how the rule of 3 naturally leads us towards smart pointers in C++. Psst, there are actually 2 more rules. And what are unique pointers and shared pointers? And how can they help Santa keep track of all those lists and even share them? So see you next time. Happy holidays.